Hello everyone, as part of learning generative AI, in the previous session we have seen what is a variational autoencoder. In this session we shall see how do we go for training of variational autoencoders, what is the decoding process and what are the applications. At least we will see some of the applications of variational autoencoders. Coming to training of variational autoencoders, it involves the forward process, then reparameterization trick, then loss function, backward pass and optimization. So these are the steps involved in training the variational autoencoders. In case of forward pass, we also call it as the encoding process. What we are trying to do is the encoder network tries to map the input data to a latent space. We know the basic functionality of an encoder, and instead of producing a single deterministic latent vector, what it does is it will try to output the parameters of data distribution, like what is the mean value of the input data, what is the standard deviation, what are the variances of various input parameters. It will try to give the distribution parameters of the input data. After this forward pass or encoding is completed, we are going for reparameterization trick. What will happen is it will allow us to go for apply gradient based optimization process. So this reparameterization trick is basically used whenever we want to apply gradient based optimization. In this, what are we trying to do is, instead of directly sampling from the distribution data, what it will do is it will try to build a particular data, or it will try to generate a particular data based on standard normal distribution values, and then once the data is ready with the standard normal distribution values, it will try to scale them to the input distribution, right. So it is like similar to what we work with normalized data whenever we are trying to generate any kind of data. In computer graphics also, we try to normalize the values between the range 0 to 1. Once I work with that normalized data, you can scale it up to match your input distribution. Then loss function, it consists of two major components. We have seen this while introducing VAEs. First one is reconstruction loss and then KL divergence loss. What is reconstruction loss? It will try to measure how accurately the decoder is trying to reconstruct an image from the compressed data. Compressed data is output of the encoder. So how well the decoder can reconstruct the data or the new data from the compressed format of the encoder. KL divergence, what it is trying to do is it is trying to regularize the latent distribution so that the distribution values are continuous and smooth, and it will be easy for interpolation. What is the overall objective whenever we are trying to talk about loss function? We are trying to minimize the sum of reconstruction loss and KL divergence loss. So always it is to minimize. Coming to backward pass and optimization, whatever gradients we are computing with respect to the loss function, they are fed back to the input parameters and we will update the values. It is somewhat like weight upgradation. You apply some weights, keep changing them for increasing the accuracy levels. You are trying to go for backpropagation techniques whenever you are trying to work with both encoder data as well as the decoder networks. How do we go for decoding in variational autoencoders? Whenever you are trying to work with variational autoencoders, the second phase of this is decoder. So what are we trying to do with? First one, latent space sampling. What do we mean by latent space sampling? The model is trained and it is trying to generate the new data. What are we trying to do is you are asking it to take sample points from the latent space. Then reconstruction. the sampled latent vectors will be fed to the decoder, and the decoder is trying to generate new data which is resembling the existing data or the training data. Interpolation, because the optimization techniques are trying to make the latent space as smooth and continuous, the interpolation becomes very easy between various points of the distribution. What are we trying to do under VAEs? We are trying to balance the reconstruction quality and regularization of the latent space. And what is the objective of this? Why are we going for regularizing the latent space? Is to produce more realistic and diverse generated samples. Let us see some of the applications of variational autoencoders. As I kept on talking in the introduction session, variational autoencoders can be used in image generation, image compression. These are the techniques wherein we can use VAEs. And whenever you are working with image generation, they try to address the applications like generating faces, objects and fashion items, right? Data imputation, it can handle the missing values very efficiently. It can fill the gap. Whenever any kind of data is missing, VAEs can automatically or easily fill the missing values. So, whenever you have such kind of situations, we go for VAEs wherein the missing values can be easily filled based on the learned patterns, right? Then anomaly detections, what it is trying to do is, it is trying to not only learn the data, it is trying to learn the distribution which is underlying the given data. So, in such cases, what it will do is, you give an outlier to it, outlier which does not fit to the training data. Whenever you try to give an outlier, what it will do is, the model should display some kind of anomalies, and it should display a kind of behavior which is not accepted. In such cases, we can identify the anomalies. If at all it is accepting that outlier, maybe the model has to be rebuilt again. You can identify the anomalies with that. Then dimensionality reduction and latent space representation, it can try to reduce the data to a lower latent distribution space. So, you can also try to see at the same time, whenever you are trying to reduce it to a lower dimensional space, you are not losing the important information. So, in such cases of visualization, clustering, feature extraction, VAEs will be used. Generative design, it can be used in the fields of fashion, architecture, product design, and wherein they are trying to go for novel variations of the designs. Similarly, it can learn the underlying patterns of the chemical compounds, and it can produce new patterns according to the needs of the people or according to the requirements of the researchers. So, we go for drug discovery and molecular design applications with VAEs. As we know, generative AI models definitely address the field of natural language processing. It can work with text generation, sentence interpolation and machine translation. These are the some of applications under NLP domain. Not only that, they can do voice and music synthesis. These days we are seeing the applications like there is a song which was sung by an old singer, and how it will be if a new singer, new generation singer is singing that one. It is very difficult for us to identify whether that particular person has really sung that song or it is an AI generated one. So, in such applications also, under music synthesis also, we are trying to work with VAEs. So, these are some of the applications wherein the VAEs are working with unsupervised learning and generative modeling across various domains. Thank you.